This talk on open access tools and datasets for AI-enabled processing of maintenance text was presented at the Mainstream Summit in Perth in March 2025. Mainstream is a popular annual conference that attracted this year over 700 participants passionate about maintenance and reliability. I've been involved with the Mainstream community for over a decade, and I'd like to thank the organisers for the opportunity to present what we have been doing in this fast-moving space. So this figure is the appropriately named MAD landscape. MAD is an acronym for Machine Learning, AI, and Data Engineering. And this is a picture of the products in this space in 2024. Picture includes many familiar names such as SAP and Microsoft. And I suggest your organization is likely using many of these products. In fact, many of them hold your data. Every time you try and go to a different application, the way the data in these applications will be represented is in a different way, with a data schema specific to that application. As a result, interoperability in the current environment is, in fact, a bit of a fantasy. So do we actually have a data crunch? And the data crunch is because we know that AI models, in general, rely on large volumes of high-quality data. The worse the data, the worse the model. When we have fragmented data infrastructures filled with unverified or poorly integrated data, this poses a systemic risk to organizations as they start to use AI. Are we facing a data crunch essentially reminiscent of the 2007 financial crisis? So just as subprime mortgages were bundled into seemingly safe packages and passed along, organizational data, often riddled with data quality issues, are now being packaged together and hidden behind the polished interfaces of Power BI applications and other reports. So it's actually probably appropriate that the solution to this is actually coming from the banking system as an example. So banks are leading the way in terms, as a sector, in terms of open shared ontologies. And at the heart of this is the FIBO ontology. And I'm going to actually walk you through the web page that describes FIBO because it nicely explains some key concepts in ontology that I'm going to draw on in the rest of this talk. So FIBO defines the set of things that are of interest in financial business applications and the ways that those things can relate to one another. Why? Because in this way, FIBO can give meaning to any data, spreadsheets, relational databases, you name it, that describe the business of finance. How does it do this? FIBO represents a consensus of the common concepts as understood in the financial industry and as reflected in industry data models and message standards. FIBO is published in a number of formats for use in business. On top of that, it is standardized and managed by an independent group, the Object Management Group, OMG. It is developed as an ontology in the web ontology language OWL. Its language is codified by the World Wide Web Consortium W3C standards, and it is based on description logic. The use of this description logic ensures that each FIBO concept is framed in a way that is unambiguous and, this is the most important part, readable by both humans and machines. So maybe some of you are listening to this and going, boy, banking has got that. We'd really love that in maintenance and reliability. So I have some good news for you. We already have an open shared ontology for manufacturing, maintenance, and supply chain data. It is managed by OAGI. OAGI is a US-based not-for-profit standards organization that's been around since 1995. It is the manager or holder of the IOF industrial ontologies. At the top of this is what's called the IOF core ontology, which is a basis for all other domain ontologies. And right now, the two published domain ontologies are one for maintenance, which we call the MRO, maintenance reliability, maintenance reference ontology, and the other for supply chain. So what are these? IOF core, MRO, and SCO reflect a consensus of the common concepts as understood in the manufacturing domain and as reflected in industry data models. It's standardized and managed by the OAGI group. They are developed as an ontology in the Web Ontology Language OWL, and languages in these ontologies are codified by the worldwide, the W3C standards. It's based on description logic, and it's aligned to the basic formal ontology, which is set out in actually an IEC ISO standard 23726 part 2. The IOF ontologies define the sets of things that are of interest in manufacturing applications and the way those things can relate to one another. In this way, the IOF family can give meaning to any data that describes the business of manufacturing and maintenance and supply chain. Just to give you a little look at what this actually means, and I know this is too small to read, but I want to just give you the colors are what's important here. At the very top of this is the BFO, top level ontology, which is widely used across the sciences and medical domains. And FIBO is a BFO aligned ontology. It's also the required ontology for alignment now for anything in US Department of Defense work and other groups there. Below this is the IOF core ontology, and that's shown in green. And I haven't shown, there are 75 classes in IOF core. I've only shown the ones that are relevant to what's in the blue boxes, which is the 20 or so classes that make up the maintenance reference ontology. The idea with the maintenance reference ontology is not that it covers all possible concepts in maintenance. The idea is that it covers concepts that are very specific to maintenance, to which other concepts can be added underneath to add more detail. I mentioned about the RDF and the OWL language, OWL and RDF. So one of the things that makes ontologies machine readable, makes all of this thing work, is that we have unambiguous, exchangeable machine readable definitions for every concept in the ontology. So for classes, for relations, and for instance data. And as an example, if you put this web address into your browser, you will get all of the information below. You will get that this is a failure process. This is what we mean by a failure process. The machine readable definitions of it in first order logic, you can see in the logical characteristics and what it relates to. And everything is described in terms of other things that also have unambiguous, exchangeable, machine readable definitions. So in this way, you and other people in your ecosystem can exchange unambiguously. Instead of just using the label failure process, you use this address and you get all of the descriptions that come from it. And this is an example of what we call linked data. Linked data is really the foundation of enterprise AI. Sometimes also known as the terms ontology and semantic web. Essentially, linked data is a data modeling and sharing paradigm that encourages and enables data interoperability, data reuse, and it ensures that your data, it helps to ensure fair data principles. Linked data is based on the open data standards, RDF and OWL, and data is formatted as triples. And an example of a triple is shown in the diagram in the middle. You can see that we have this idea of a subject, a node that is a subject. We have a node that is an object, or in fact a data type. And then we have these connectors or predicates in the middle so that we can say this pump is of manufacturer Grundfos, and it has a flow rate of 100 liters per second. And all our data is stored in this according to this RDF data modeling paradigm. And as you can see, inside each of those boxes is a URI address. So we have two things here. We have both the way we're describing it as the triple, and the fact that everything in that triple may have a label, but it also has this URI address. And it is this combination that unambiguously defines the data concepts that we use in our business. What does this mean in terms of enterprise AI? This means that those data sources that are either stored internally in your various databases, or as data that is stuck inside various applications that you own, this data can be lifted into a semantic layer in your organization and then exposed as linked data for use in your own internal applications, or indeed shared with others in a controlled way. And this is why linked data is really at the foundation, because it's the foundation of this semantic layer. So what are the three common preconditions for enterprise AI? So first of all, obviously, you can't be using lots of different terms to describe the same thing. That confuses humans, and it certainly confuses AI. So really, for long-term AI success, enterprise software systems, AI systems, and humans need to speak the same language. And this is enabled by alignment to common ontologies. You've got to ground the data so that we can make use of, some of these fantastic large language models and RAG and other techniques that are coming up. But you need to be able to ground those and search them effectively, and having good schemas really helps with that in order to ground both the model and how it performs, and also to check the results. And we also know that there is more types of AI than just large language models, but large language models specifically have this hallucination problem, and the linked data paradigm offers and provides the opportunity for reasoning, data constraint, and other checking techniques to support data validation. So I mentioned in the abstract that I was going to talk a little bit about the some of the experience of the UWA NLP-TLP group with enterprise AI and language models. And I've just divided these broadly into three groups. Company organizations we've worked with on what we consider narrow AI problems. So these are problems where you built a very specific model for a very specific application in a defined space, like a classification model. Can we classify failure modes, for instance? Can we clean data? Can we translate dirty data to clean data? And those are the organizations that have really collaborated with us in those areas. Moving to the bottom, obviously, since ChatGPT came out, we've done a fair amount of work in the generative AI space, and this is in the main been with trying to get complex, get information and query long, complex technical reports with government bodies, and but core as well, Merrower, and GSSA. But also recently, a very exciting project that's ongoing with South 32, where we're starting to look at safety records and long and, obviously technically heavy safety records. And then the third area that we're working on is with these ontologies and for semantic interoperability. And almost all of that work up until now has been with a consortium of people in Northern Europe, in the Scandinavian and German countries. And I'm going to talk a little bit more about that. But I also have a project right now with CSIRO, which is quite exciting. So the UWA NLP-TLP group, we kind of like to think local and act global. We were founded in 2018. We have had about $1.8 million worth of cash funding. A very significant part of this came from our participation in the Center for Transforming Maintenance Through Data Science, which was a 5-year government and industry funded center, a fantastic experience for us. And we are very grateful to the partners in that center, BHP, Alcoa, Roy Hill, Merrower, Core, and Cyro. And out of that, we not only developed a whole suite of open source tools and data sets, particularly what I'm going to talk about is the Menti annotated data set. We have developed many GitHub repos where you can get open source examples of various things we've done. We've also developed a lot of capabilities. So we've had 6 amazing PhD students, a whole suite of honors and master's students. And then in addition to this, we've also participated in these global efforts with multi-country efforts to develop the IOF maintenance reference ontology, maintenance activity, the maintenance procedure, and the FMEA ontology. And also we're participating, I myself and Kate Woods are currently very active in this new ISO industrial data ontology. So these slides are going to be made available. So I've got a whole bunch of links here to some tools that you might want to check on later on. These include, for example, the Quick Graph tool, which is a web-based tool that a number of organizations are using to annotate particularly maintenance texts for training transformer models. LexiClean, which is an amazing tool if you want to annotate data in order to provide training data for cleaning noisy corpora. Mudlark, which is a nice little Python package for the simple cleaning of CSVs. Anyway, the list goes on. I encourage Menti, which I will talk about a little bit more, which is the world's largest fine-grained annotation schema and benchmark to translate your maintenance short text into very high quality knowledge graph, annotated knowledge graph for querying. And you can just run your data through that. So what I'm going to do now is just give you some ideas about how AI language models can deliver business value. So for me, in the maintenance world, one of the most important things is to just make it a lot easier for people to get good, rich, clean, consistent data out of maintenance records. There's so much useful information is in maintenance records. And if you think about, just maybe taking a minute to say, why do we do this? We do this because we are absolutely laser focused on making sure that the people at the front end, the maintainers on the tools are doing the right work at the right time in the right way. This only happens if we've set things up for them. We have good and appropriate strategies targeted at things that do really have those failure modes. That we're giving them the right procedures that are up to date, that have the right tools. All of these information we need to be pulling from and updating from maintenance texts, be they procedures or work orders or the like. If these things are a nightmare and people that process them do them differently, or they use inappropriate codes because the coding system is inconsistent, this is going to cause problems downstream. So at the heart of all of this is making sure at least we are reducing the effort required by reliability engineers and planners and whatever to find and extract information. And actually, they shouldn't be doing that at all. They should just be able to query the information and not go back and have to look at all the work orders. But the first step in being able to build a graph or this semantic layer in order to allow them to query it is to translate the dirty to clean texts. And we have three really main tools for this that are, as I said, open source, and you can go and use them tomorrow. First of all, we have Mudlark, which is a Python utility, as it says there. We have the LexiClean collaborative annotation tools, so you can agree how you want to clean data, produce a training set, an annotated cleaning set, and then clean your own corpus, and that works on any type of data. And then specifically for maintenance work order short text, we have some examples here of the black is dirty text and the blue is clean text. And you can just use that model. You just pass your data into that model and you will get the clean text. Go give it a go. As I mentioned earlier, rather than have maintenance engineers or reliability engineers or planners query data by going right back to the SAP records or the CSVs that come out of that or whatever. What we really want to do is get them to write a query that says, for example, what are my which assets have most highest cost of lubrication in the last month? You can write that query, and we can get an answer from that from 800,000 maintenance work order records. How do we do this? Is we build company-specific knowledge graphs aligned to a schema, which is constructed to answer the sorts of questions that I've just illustrated. In this case, as a starter, we have the Mainty annotated work order corpus. You can use that to train a SPERT or other transformer model to identify all the physical objects, failure modes, and the relationships from component level to flock. This is a part of this, is a part of this, is a part of this, and failure mode to component. That we provide that in the GitHub, both the corpus if you want to do it yourself and the model. Then you can fine tune it on your own company annotated to make sure it uses the sort of equipment, it reflects the sort of equipment that you have, and maybe in some of the particulars of your own maintenance work orders. And organizations have done this, including one of the major partners, some of the major partners in our Center for Transforming Maintenance Through Data Science. One of the things I would say about the knowledge graph that we produce in this way is it allows you to query at the component level and at the observed state. You are no longer limited in your queries to the lowest level of the flock system. We go all the way from whatever your lowest level of the flock system, say that is something like on a conveyor, a pulley, but doesn't go down to head and tail pulley, or doesn't go down to individual idlers maybe. We can go to that level and see what the observed state is on that level. And we can do that for hundreds of thousands of maintenance work orders. And we've also done it for one particular partner in terms of their strategies. As I mentioned earlier, one of our earliest sort of focus areas was to automate one of the most completely boring and poorly done tasks that reliability engineers do, which is to classify failure modes in maintenance work orders to a classification scheme. And this is sort of an illustration of just how fast the world is changing. This work is now 2 or 3 years old. We would probably do even better now than we did back then. But we had a set of failure mode codes. We can query it. We can, when we did this just with a transformer model, we got so-so results. When ChatGPT came out, and so remember this is back a couple of years right now, we wrote some prompts and we did the same thing. And again, the results were very average. Then we took our fine-tuned schema. We took our schema and ChatGPT, and the combination of having a schema and the large language models, and we're getting amazing results, way better than we would get if we had 3 reliability engineers do the same job. For anybody who's interested, there is a lovely demo on this YouTube site, and also a paper you can look, and of course the code is also available. One of the major bits of work that we have done is on semantic quality assurance of maintenance procedures, and this has been the focus of Caitlin Woods in her PhD. And there is too much to describe here, but what I think we all appreciate with maintenance procedures is that they're very the digitization and the management and design of the digitization and keeping them update and correct and complete is problematic. What we have been doing here is really 2 things. The first thing is developed an ontology for maintenance procedures that we can map the key concepts in a procedure to, so that we can do some semantic quality assurance, like, is this procedure complete? Is it correct? And is it consistent? But on top of that, with the ontology, we can also start to support the maintainer in terms of the work that they're doing in real time, or the planner, in terms of the content of what's in those procedures. For example, we could have queries that say, what tools, materials, and permits do I require to execute this particular procedure? And that would be the query to the knowledge graph, and it would return all of the information you need without having to go and find the procedure itself. And you can see some examples of other steps. These examples are, as I said, we considered different stakeholders here, but really this is about digital tablets for maintainers and about supporting the planners. And of course, supporting the people who manage the procedures. Now we move a little bit to the logic AI, and it's been a really fantastic opportunity for me personally over the last few years to work with this group in Northern Europe that has for some years been developing ontologies and shared data models to allow them to exchange design data through the design process rather than as data models rather than PDFs. And so in the companies at the bottom, we have Equinor, which is a fairly major energy company in Norway. We have Able, which is an EPC engineering procurement engineering design house. We have suppliers such as Grundfos and Siemens, and we have DNV, which is an assurance house. And then I've put ISO in there because what we are doing here is the data model that is at the heart of all of this work is on its way. It's to be an ISO standard and should be published as an ISO standard later this year. So it will be openly available for a price to anybody in industry. And this is shared data model enables the ecosystem for sharing to get away from PDFs. I should say that in the course of this, we are also working on extracting information from ISO API and ASME standards in order to make sure that they are also in the same data modeling structure and can be used as such. And so this is broadly what the ecosystem as we have now looks like. We have the blue bit in the middle. We have the data models that are semantically interoperable. Our EPCs, the operators, and the vendors can provide us with information from their internal commercially, commercial and confidence data. They can provide the data needed for whatever job is being required. That data is structured based on the things in the green boxes. So the industrial data ontology 23726 part 3, various domain independent reference ontologies, for example, GeoSparkle, the time ontology, and other useful things that's the semantic sensor network ontology that are freely available. Reference ontologies and modeling patterns for standards, that's the work I mentioned with API and ASME that we are doing on their standards. And people can reuse templates that make this all very easy. Now, once we have that in there, this completely changes how the nature of the interaction, and it really speeds it up and provides all sorts of quality assurance opportunities. And I'm just going to give you one which I rather hope will blow your mind. So we're involved in doing some demonstration about engineering design verification. So on the left, you see a typical spec from an Equinor valve design spec, or VDS, and this is publicly available on their TR2000 website. And you can see this is a really complex set of requirements to do with the valve design, the materials that can be used, is the size, the class, the pressure, the temperatures, and all of that. This is information in here is lifted into into essentially something that maps the valve design ontology and a whole set of actually modular ontologies. And when these all fit together, because they are aligned to this top level IDO 23726 part 3 ontology, And we can then, for example, take a product supplied by a vendor, and in this case, on the right at the very top, you can see something called the OMS Salieri valve. And our question is, does this valve, which has these characteristics in the sort of white background on the right, is it compliant with the BCAS 302R valve design specification on the left? And we run what's called an ontology reasoner, and the yellow shaded things that you see on the right-hand side come back from the reasoner, and they tell us, yes, indeed, this Salieri valve is in fact compliant with the specification on the left, and not just compliant with what the things you can see in that specification, but compliant with the information that this specification refers to in all the tables of the attached standards. So each of those standards that's mentioned there is about 200 pages long. So normally a piping engineer has to both look at the TR2000 and then go and find the specific table in the specific standard in order to do this. Instead, with this setup, we can now run these checks automatically. It is a mind-blowing game changer for the engineering design space. It's a very exciting time. It's very exciting to be part of this. So I hope I've given you a few ideas about how what's going on in the maintenance and reliability space, and the focus here on developing open tools, and those can be open source and freely available on GitHubs, like the maintenance tools that I've been talking about that have come out of the UWA NLP-TLP Center and the Center for Transforming Maintenance through Data Science, but also these developments in the ISO standard space where things are open and shared, but obviously they're not free. And then there's a bit of a sigh, because everybody will be thinking, yes, of course, we'd love to do that, but there are a million reasons we can't use any of this stuff. And it was interesting that the day before Mainstream, something popped up on my LinkedIn. A post popped up from an information artifact who works for Adobe. And I'll share with you what she said. I used to face a lot of resistance in organizations when I introduced taxonomies, ontologies, and knowledge graphs. Why? Because, people said it will take too long. Oh, I don't have time to do this. We don't have the people. Can't we just machine learning do all of this to us? And, doesn't some magic happen? Or, oh, what the hell wrong with what we do right now? And she makes the point, rightly so, that the reality is that the data collection and hoarding practices just continue to chain us to rigid database systems. And in a world where we have graph and linked data options, we have to look beyond this. We cling to what was rather than investing in what could be. Please think on that. But I have to also say that when it comes to the ontology pipeline, working with ontologies is not fast. True parts of the work can be automated, but not all. The work needs ontologists and graph specialists. It's constant and continuous, and it needs humans in the loop. And rather, like asset management itself, working with ontologies is not a diet, it's a lifestyle change. So what could the future look like for you? Potentially, in your organization, you could have a pyramid of ontologies and schemas. At the top, you decide which top-level ontology you want to align to. And I work with both the IDEO ontology group and the IOF and BFO ontology group. There's not, one is more geared towards the engineering design space, that would be IDEO, and the other is more geared in my mind towards the maintenance and reliability space. But I'm happy to talk more about that. Underneath that, you select and work with domain-independent ontologies that are just there and make your life so much easier, because they have a bunch of Lego bricks that you can reuse. Because ontology concepts are like Lego bricks in terms they have dimensions, interfaces, purpose. And the whole idea is that if everybody makes their own type of brick without a shared specification, bricks don't work together. We have the chaos we have now with the MAD schema. But how do we make sure that we're all making Lego? Well, we have to conform to the Lego schema. And in the enterprise AI world, what this means is we need to conform to a top-level ontology. So choose one. Once you've chosen one, you can make new bricks that hook into the existing setup, provided they conform to your specification, and you can reuse existing bricks. And if by chance somebody in your organization makes a brick that doesn't connect to anything else, you find that out when you run the reasoner. And so we've got this whole sort of reusable brick setup which you can start to use already. We already have and are using domain-independent ontologies. We already have and are using the IOF core, the IOF maintenance, and other domain-specific ontologies. We have industry standards in the engineering design space. We have made various versions of these standards. And this year, I'm working on making a machine-readable version of the ISO 14224 standard, which I know a number of people use. And then below that, you can configure your company data to use company-specific schemas and ontologies, and then your asset individuals can be lifted into this, and things can work in an interoperable manner. So in closing, I have some final observations. So my observation is that AI adoption is incredibly fragmented in the maintenance space. I think that there is a lot of opportunity for very useful but unexciting applications like data cleaning and data quality checks. And I know that's difficult to sell to executives, but it's incredibly foundational, and you're not going to move fast without those, fast or far without those as you do AI. I urge you to reuse and build on what is already here. Have a look at what I've shown you today. It works. It's usable. Have a go. As I have tried to stress, once you're getting to the interoperability piece, to scale, you're going to need to align data models to reusable schemas aligned to a top-level ontology. We know this from the banking industry. We know this from other sectors as well. None of this happens without sustained leadership. A one-year project is not going to get you over the line here. You need to build internal capability, both for the AI, narrow AI work, the Gen AI work, and if you're interested, the logic AI work. The logic getting in ontologies will cost you money, just because of the capabilities and the transformation and need to involve the software architects. And then finally, a bit of a note, which from the CTO of the AI group in IBM, to remind us all that in this fast-moving space, AI is not going to replace managers, but managers who use AI are going to replace those that don't, because they're going to enable their team to be so much more productive and efficient. Use the skills and the technical skills they have to do analysis, rather than just spend a whole bunch of time processing data. So I hope you've enjoyed that. Here are some contact details for LinkedIn for the NLP-TLP site. And then we've recently made a couple of playlists for YouTube recordings. The first one relating to NLP and knowledge graphs, and the second one for the ontology work I've just talked to you about. So I hope you look at those and enjoy them. Thank you very much.